The gun method is roughly how the Little Boy weapon, which was detonated over Hiroshima, worked, using uranium-235 as its fissile material. In the Little Boy design, the U-235 bullet had a mass of around 86 pounds (39 kilograms), and it was 7 inches (17.8 centimeters) long, with a diameter of 6.25 inches (15.9 centimeters). The hollow cylindrical shape made it subcritical. It was powered by a cordite charge. The uranium target spike was about 57.3 pounds (26 kilograms). Both the bullet and the target consisted of multiple rings stacked together. The use of rings had two advantages. It allowed the larger bullet to confidently remain subcritical, the hollow column served to keep the material from having too much contact with other material, and it allowed subcritical assemblies to be tested using the same bullet but with just one ring. The barrel had an inside diameter of 6.5 inches (16.5 centimeters). Its length was 70.8 inches (1.8 meters), which allowed the bullet to accelerate to its final speed of about 1,000 feet per second, 300 meters per second, before coming into contact with the target. When the bullet is at a distance of 9.8 inches (25 centimeters), the combination becomes critical. This means that some free neutrons may cause the chain reaction to take place before the material could be fully joined. See nuclear chain reaction. Typically the chain reaction takes less than 1 microsecond 100 shakes, during which time the bullet travels only 0.3 mm. Although the chain reaction is slower when the supercriticality is low, it still happens in a time so short that the bullet hardly moves in that time. This could cause a fissile, a pre-detonation which would blow the material apart before creating much of an explosion. Thus it is important that the frequency at which free neutrons occur is kept low, compared with the assembly time from this point. This also means that the speed of the projectile must be sufficiently high. Its speed can be increased, but this requires a longer and heavier barrel. In the case of Little Boy, the 20% U-238 in the uranium had 70 spontaneous fissions per second. With the fissionable material in a supercritical state, each gave a large probability of detonation. Each fission creates on average 2.52 neutrons, which each have a probability of more than 1 to 2.52 of creating another fission. During the 1.35 milliseconds of supercriticality prior to full assembly, there was a 10% probability of a fission, with somewhat less probability of pre-detonation. Initially the Manhattan Project gun-type effort was directed at making a gun weapon that used plutonium as its source of fissile material, known as the «Thin Man», because of its extreme length. It was thought that if a plutonium gun-type bomb could be created, then the uranium gun-type bomb would be very easy to make by comparison. However, it was discovered in April 1944 that reactor-bred plutonium, Pu-239, is contaminated with another isotope of plutonium, Pu-240, which increases the material's spontaneous neutron release rate, making pre-detonation inevitable. For this reason, a gun-type bomb is thought to only be usable with an enriched uranium bomb. After it was discovered that the «Thin Man» program would not be successful, Los Alamos redirected its efforts into creating the implosion-type plutonium weapon, Fat Man. The gun program switched completely over to developing a uranium bomb. Although in Little Boy 132 pounds 60 kilograms of 80% grade U-235 was used, hence 106 pounds or 48 kilograms, the minimum is about 44 to 55 pounds 20 to 25 kilograms, versus 33 pounds 15 kilograms for the implosion method. The scientists who designed the «Little Boy» weapon were confident enough of its success that they did not field test a design before using it in war, though scientists such as Louis Slotin did perform non-destructive tests with subcritical assemblies, dangerous experiments nicknamed tickling the dragon's tail. In any event, it could not be tested before being deployed, as there was only sufficient U-235 available for one device. Even though the design was never proof-tested, there was thought to be no risk of the device being captured by an enemy if it malfunctioned. Even a fissile would have completely disintegrated the device, while the multiple redundancies built into the Little Boy design meant there was negligible if any potential for the device to strike the ground without detonating at all. For a quick start of the chain reaction at the right moment, a neutron trigger initiator is used. An initiator is not strictly necessary for an effective gun design, as long as the design uses target capture. In essence, ensuring that the two subcritical masses, once fired together, cannot come apart until they explode. Considering the 70 spontaneous fissions per second, this only causes a delay of a few times 1/70th second, which in this case does not matter. Initiators were only added to Little Boy late in its design. With regard to the risk of proliferation and use by terrorists, the relatively simple design is a concern, as it does not require as much fine engineering or manufacturing as other methods. With enough highly enriched uranium, nations or groups with relatively low levels of technological sophistication could create an inefficient, though still quite powerful, gun-type nuclear weapon. For technologically advanced states, the gun-type method is now essentially obsolete, for reasons of efficiency and safety discussed above. The gun-type method was largely abandoned by the United States as soon as the implosion technique was perfected, though it was retained in the specialized role of nuclear artillery for a time. Other nuclear powers, such as the United Kingdom, and the Soviet Union never built an example of this type of weapon. Besides requiring the use of highly enriched U-235, the technique has other severe limitations. The implosion technique is much better suited to the various methods employed to reduce the weight of the weapon and increase the proportion of material which fissions. South Africa built around 5 gun-type weapons, and no implosion-type weapons. They later abandoned their nuclear weapon program altogether. They were unique in their abandonment of nuclear weapons, and probably also by building gun-type weapons rather than implosion-type weapons. There are also safety problems with gun-type weapons. For example, it is inherently dangerous to have a weapon containing a quantity and shape of fissile material that can form a critical mass through a relatively simple accident. Furthermore, if the weapon is dropped from an aircraft into the sea, then the moderating effect of the seawater can also cause a criticality accident without the weapon even being physically damaged. Neither can happen with an implosion-type weapon, since there is normally insufficient fissile material to form a critical mass without the correct detonation of the explosive lenses. The gun method has also been applied for nuclear artillery shells, since the simpler design can be more easily engineered to withstand the rapid acceleration and g-forces imparted by an artillery gun, and since the smaller diameter of the gun-type design can be relatively easily fitted to projectiles that can be fired from existing artillery. A U.S. gun-type nuclear artillery weapon, the W-9, was tested on May 25, 1953 at the Nevada test site. Fired as part of Operation Upshot Knothole and codenamed Shot Grable, a 280 mm shell was fired 10,000 meters and detonated 160 meters above the ground with an estimated yield of 15 kilotons. This is approximately the same yield as Little Boy, although the W-9 had less than 1/10 of Little Boy's weight, 365 kilograms versus 4,000 kilograms, or 805 pounds versus 8,819 pounds. The shell was 1,384 mm long. This was the only nuclear artillery shell ever actually fired from an artillery gun in the U.S. test program. It was fired from a specially built artillery piece, nicknamed Atomic Annie. 80 shells were produced from 1952–53. It was retired in 1957. The W-19 was also a 280 mm gun-type nuclear shell, a longer version of the W-9. 80 warheads were produced and the system was retired in 1963. The W-33 was a smaller, 8-inch (203 mm) gun-type nuclear artillery shell, which was produced starting in 1957 and in service until 1992. 2 were test-fired detonated, not fired from an artillery gun, 1 hung under a balloon in the open air, and 1 in a tunnel. Later versions were based on the implosion design. Bombs Little Boy, 1945–1951 Thin Man, cancelled Mark 8, Bunker Buster, 1952–1957 Mark 10, cancelled Mark 11, Bunker Buster, 1956–1960 Artillery W-9, 1952–1957 W-19, 1955–1963 W-23, 1956–1962 W-33, 1957–1992 Other T-4 atomic demolition munition, 1957–1963 W-8 for the SSMN-8 Regulus cruise missile, cancelled.